Today we are going to look at a number of rules that will help us take derivatives or compute derivatives of functions very quickly. So these are the rules that are literally the calculus of calculus. So these are the rules and techniques that allows us to take derivatives of complicated functions rather easily. So no complex, complicated limits involving the formal definition of a derivative. We can just apply all of these rules and take the derivative of more and more complicated functions. So the first rule is a very basic rule that immediately extends our ability to take derivatives of functions and build more complicated or more complex derivatives from known derivatives. And these are the so-called linearity rules. So let me say linearity rules. So basically, in mathematics, you might say the derivative is a linear operator. And what that means is that it has two basic properties. So the first property is that the derivative, so d by dx, of a constant times f of x is equal to that constant times the derivative of f of x. In other words, when you're taking the derivative of a function, you can pull a constant outside of the derivative. So instead of taking the derivative of some number times the function f, you can just, if you already know the derivative of the function f, you can just multiply the derivative by the number k. So basically, scalars or constants are free agents that can move into or out of the derivative sign for free. And the second rule is that the derivative of the sum of two functions, so suppose we have f of x plus g of x, is just equal to the derivative of f of x plus the derivative of g of x. So in other words, the derivative of a sum is the sum of the derivatives. So the derivative acts separately on different terms, on each term of the sum. Now, these are the main two rules, and these are actually entirely equivalent to saying that the derivative of, maybe I'll say a times f of x plus b times g of x is equal to a times f prime of x plus b times g prime of x. So in other words, you can pull apart the two terms, and then you can pull the constants out of the derivatives as well. So either these two rules or this rule, you can trade this rule for these two up here, or these two rules for this. So these two rules actually imply this rule down here, and this rule down here implies the two rules up there. To see why these rules are true, we just have to look at the limit definition of the derivative. So the derivative of k times f of x, by definition, is going to be the limit as h goes to 0 of k of f of x plus h minus k times f of x over h. Now there's a common factor of k on both of these terms, so you can pull it out. So you can rewrite this as the limit as h goes to 0 of k times f of x plus h minus f of x. We'll put some parentheses around that, and then all over h. Right, so k is we have a factor of k in each of these terms, so you can pull it out. Now k is a constant, right? It could be like the number 5. So we can move that guy out of the limit because you can move a constant outside of the limit. So this in turn is just equal to k times the limit of f of x plus h minus f of x over h. So that's just k times f prime of x. And similarly, if you have the derivative of f of x plus g of x, let's see how that one works. Actually, let's get rid of all of this. So if we take the derivative of f of x plus g of x, so that's going to be the limit as h goes to 0 of this function, which is the function f plus g first, f of x plus h plus g of x plus h. Right? So that's the function f plus g evaluated at x plus h, and then minus the function x plus g evaluated at just x. And clearly you can rearrange this so you get f of x plus h minus f of x, and then over h, and then plus g of x plus h minus g of x over h. So you can rearrange this as the limit as h goes to 0 of f of x plus h minus f of x over h plus g of x plus h minus g of x over h. Now, as long as this limit and this limit both exist, you can separate the limits. Just like this. And then this is, of course, just equal to f prime of x plus g prime of x, just like that. So the caveat here is that if f and g are differentiable. In other words, if the derivatives are defined at a given point, if f prime and g prime are defined, then these two rules hold, like that. So I'll give you an example. I'll say we have a few derivatives that we know, so I'll provide a few derivatives for free. So the derivative of x to the fourth is 4x cubed, and the derivative of x squared is 2x. Okay, so then using that information, can we compute the derivative of 3x to the fourth plus 8x squared? Well, using the derivative rules, this derivative acts linearly. In other words, what we have here is a constant coefficient. So this is a coefficient and a coefficient, and then it's a sum. So this guy, the coefficients come out of the derivative, and the derivative acts on each term separately. So just showing you all the steps, it's the derivative of 3x to the fourth plus the derivative of 8x squared. And then next, we can pull these constants out as well. So we get 3 times the derivative of x to the fourth plus 8 times the derivative of x squared. Now, given derivative of x to the fourth is 4x cubed. 4 times 3 is 12, so we get 12x cubed. And then the derivative of x squared is 2x, so 2 times 8 is 16, 16x like that. Now, normally I wouldn't write these two steps out. I would just go directly from here to there. But this is kind of what's happening in your head. Okay, well, the derivative gets applied separately to each term, so I just have to look at this term. What's the derivative of this term? 4 times 3x cubed, so 12x cubed, and then plus, let's go to the next term. What's the derivative of that term? And it's going to be, the 2 comes down, 16x, so it's just 16x like that. So basically, when we take the derivative of 3x to the fourth, we just ignore the 3. You just focus on, well, what's the derivative of x to the fourth? It's 4x cubed, so the derivative of 3x to the fourth is 12x cubed. And then you just do each term individually. So that's the power of the linearity rules.